Quantum physics has a mystique of being complicated and hard to understand. In fact, Richard Feynman, who won the Nobel Prize for his work on quantum electrodynamics, said, "If you think you understand quantum physics, you don't understand quantum physics." Which is kind of disheartening for us, because if he didn't understand it, what chance do the rest of us have? Fortunately, this quote is a little misleading. We do in fact understand quantum physics really well. In fact, it's arguably the most successful scientific theory out there, and has let us invent technologies like computers, digital cameras, LED screens, lasers, nuclear power plants. And you don't really want to build a nuclear power plant if you don't really understand how it works. So quantum physics is the part of physics that describes the very smallest things in our universe. Molecules, atoms, subatomic particles, things like that. And things down there don't quite work the same way that we used to up here. This is fascinating because you and everything around you is made from quantum physics. And so this is really how the whole universe is actually working. I've drawn these protons, neutrons and electrons as particles, but in quantum mechanics we really describe everything as waves. By the way, I'm using quantum physics and quantum mechanics interchangeably, they're the same thing. So instead of an electron looking like this, it should look something like this. This is called a wave function. But this wave function isn't a real physical wave like a wave on water or a sound wave. A quantum wave is an abstract mathematical description. To get the real-world properties like position or momentum of an electron, we have to do mathematical operations on this wave function. So for the position, we take the amplitude and square it, which for this wave would look something like this. This gives us a thing called a probability distribution, which tells us that you're more likely to find the electron here than here. And when we actually measure where the electron is, an electron particle pops up somewhere within this area. So with quantum physics, we don't know anything with infinite detail. We can only predict probabilities that things will happen. And it looks like this is a fundamental feature of the universe, which was quite a departure from the clockwork deterministic universe in classical physics, the kind of thing Newton derived. This wave function model predicts what subatomic particles will do incredibly well, but weirdly we've got no idea if this wave function is literally real or not. No one's ever seen a quantum wave because whenever we measure an electron, all we ever see is a point-like electron particle. So there's like this hidden quantum realm where the waves exist, and then the world we can see, which is where all the waves have turned into particles. And the barrier between these is a measurement. We say that a measurement collapses the wave function, but we don't actually have any physics to describe how the wave collapses. This is a gap in our knowledge that we've dubbed the measurement problem, and this is one of the things that Feynman was referring to with his quote. Another confusing thing is how exactly to picture an electron. It seems to be a wave until you measure it, and then it's a particle. So what actually is it? This is known as particle-wave duality, and here's an example of it in action, the famous double-slit experiment. Imagine spraying a paintball gun at a wall with two openings in it. You'd expect to see two columns of paint go through and hit the wall behind. But if you shrink this all down to the size of electrons, you see something quite different. You can fire one electron at a time at the slits, and they appear on the back wall. But as they build up over time, you get a whole pattern of stripes instead of just two bands. This pattern of stripes called an interference pattern, something you only see with waves. The idea is that it's the electron wave that goes through both slits at the same time, and then the waves from each slit overlap with each other, and where the waves add together you've got a high probability of the electron popping up at the wall, but where the waves cancel out the probability is very low. So actually on the back wall the highest probability of finding the electron is in the middle of the slits, and then it goes down and then up again and down and up again, and this is the interference pattern. So when you fire one electron after another, they follow this probability distribution, and this interference pattern starts building up, and that's exactly what we see in experiments. So this shows that electrons behave like waves in this experiment. The question is, what actually happens to this spread out electron wave when you do a measurement? It seems like it goes from this spread out wave to this localized particle. But like I said, there's nothing in quantum mechanics that tells us how the wave function collapses. And this is not only true for electrons, but everything in the universe. So this double slit experiment has huge consequences for our model of the universe. And it was very surprising the first time it was done. Physicists are still grappling with this question today and have come up with many interpretations of quantum mechanics to try and explain these results and explain how reality actually works. Okay, let's go back to the wave function. We can now use this picture to explain other features of quantum physics that you may have heard about. So this is just one possible wave function for an electron, but there's many others, like this one for instance. This says that the electron has a probability of being over here and a probability of being over here, and very little probability of being in the middle. This is perfectly allowable in quantum physics, and this is where the phrase "things can be in two places at once" comes from. This is known as superposition, which comes from the fact that this wave can be made by adding, or superimposing, these two waves. The word superposition just means the adding together of waves, and we already saw this in the double slit experiment. And it's not really a very special phenomenon. You can even see superposition by dropping two pebbles into a pond where the ripples overlap. Now for entanglement. Let's say two electron waves meet. Their waves interfere with each other and become mixed up. This means that mathematically we now have one wave function that describes everything about both electrons, and they're inextricably linked, even if they move far away from each other. A measurement on one of the particles, like measuring if it's spin up or down, is now correlated with a measurement on the other, even if they move billions of miles away. Einstein was very uncomfortable with this idea because if you measure one of the particles here, you instantaneously know what the other will be, even if it's billions of miles away. And that's got a sort of whiff of faster than light communication, which is not allowed by the theory of relativity. But it turns out you can't actually use this to communicate information because the measurements give you random results. But the fact that they are correlated means that somehow there is a link that stretches over that distance. This is called non-locality. Quantum tunneling. Quantum tunneling is where particles have a probability of moving through barriers, essentially allowing things like electrons to pass through walls. When a wave function meets a barrier, it decays exponentially inside the barrier. But if the barrier is narrow enough, the wave function will still exist on the other side, meaning that there's a probability of the particle being found there when a measurement is made. In fact, the only reason you're alive is because of quantum tunneling in the sun, which makes the sun shine. Protons normally repel each other, but they've got a small probability of quantum tunneling into each other, which is what turns hydrogen into helium and releases fusion energy. All life exists on Earth because of energy from the sun, except for life around hydrothermal vents. Now onto the Heisenberg uncertainty principle. I said at the beginning that this wave function contains all of the information like position and momentum of the electron. We just have to do some maths on it. The position is given by the amplitude or height of the wave, and the momentum is given by the wavelength of the wave. But for this specific wave, the position gives us a probability distribution, so we don't know exactly where the electron is. Also, there's an uncertainty in the momentum because this wave is made of many different wavelengths. But we can reduce that uncertainty. Let's have a wave that only has one wavelength, so a sine wave. Now we know the momentum exactly because the wavelength has a single value. But look at the position. There's an equal probability of the electron being found anywhere in the universe. Okay, let's do the opposite. Let's make a wave that has only one position. Now we know exactly where the electron is, but what's the wavelength of this wave? Now the wavelength is very uncertain. Basically, only a sine wave gives you a precise momentum. And any wave that isn't a perfect sine wave, you have to build out of multiple different sine waves. And each of those multiple different sine waves has got a different wavelength, and hence you have a range of the possible different values of momentum for the particle. This is Heisenberg's uncertainty principle. You can only know certain things precisely, but not everything. Either you've got a definite value of momentum and don't know anything about position, or you know the position very well, but don't know anything about the momentum. Or you're in some intermediate state. And this isn't a limit of our measuring apparatus, this is a fundamental property of the universe. And finally, where does the name quantum come from? Well, a quanta is a packet of something, like a chunk of something. And one of the first quantum effects people saw were atomic spectra, which is where atoms give off light with specific discrete energies. It works like this. Imagine a string that's tied at both ends, like a guitar string. If you pluck it, only certain waves can exist because the ends are tied down. In this situation, we say that the wavelengths are quantized to certain values. The same thing happens if you tie the ends of the string together because the waves have to match up. They can only vibrate in certain restricted ways. And this is what's happening to an electron in an atom. The electron wave is constrained by the atom and quantized to certain wavelengths. Short wavelengths have got a high energy and long wavelengths have a lower energy. This is why the light emitted by an atom looks like a barcode, because each bar of light corresponds to an electron jumping from a wave with a high energy to one with a lower energy, and at the same time emitting a quantized photon of light when it does this. So the light from an atom is quantized to discrete packets of energy. Okay, so that's all the basics of quantum physics. Here are some technical notes which aren't essential to know, but pause the screen now if you're interested in a little bit more mathematical detail. So to round up, in quantum physics objects are described with wave functions, but when we measure them, what we see are particles. So this leads to particle-wave duality and also the measurement problem. And the consequence of these wave functions are the quantum phenomena of superposition, entanglement, quantum tunneling, the Heisenberg uncertainty principle, and energy quantization. So if you understand these things, you've got a good basic understanding of quantum physics. Despite its reputation, I think that quantum mechanics isn't too difficult for most people to get the basics of what's going on. In the past I've relied on analogies to try and explain it, but here I've just described what's actually going on, which I think might be more helpful. But if you've got more questions, I'll be on the comments below, so ask away. For me, the weird thing about quantum physics is that on the one hand it's incredibly accurate and predictive, but also it's got giant holes in it like the measurement problem, which we just don't understand. So we can wonder, will we ever actually understand quantum physics, or is it just too abstract for our human brains to comprehend? Well, I hope this video has helped you understand a little bit more about how quantum physics works. And thanks to the sponsor of this video, Brilliant.org, who have just launched their daily problems, which you can dip into if you've got a spare 5 minutes each day. Each problem teaches you some interesting facts that you can then use to solve the problem. And if you enjoy that specific problem, there are links to more on the same topic, so you can develop your framework of knowledge around that subject. And as ever, if you're confused and need more guidance, then you can join with the community discussions. So this is a simple, fun way to keep learning more. If that sounds interesting, go to brilliant.org/DOS or click on the link in the description below, and the first 200 to do so will get a 20% discount off the annual subscription, which unlocks all of their premium content. Well, that's it from me. Thanks for watching, and I'll see you next time.